In this highlight video, we are going to use what we've learned about substitution reactions to predict the products in reactions that we haven't seen before. So after you've watched this video, you will be able to identify the likely mechanism of a substitution reaction and be able to predict the major products. In order to do this, we need to consider the different reaction components. We will consider the alkyl group of the alkyl halide, the nucleophile, the leaving group, and the solvent. We'll go through these and remind ourselves what we've learned about these different components in this order. Remember, for alkyl halides, we have two effects that influence the mechanism. One is the steric strain, and the second one is the stability of the carbocation intermediate. Okay, steric strain plays a role predominantly in SN2, and of course the carbocation only plays a role in SN1. So what we learned before is that if we have methyl halides or primary alkyl halides, they will only do SN2 substitution reactions. If we have tertiary alkyl halides, they will only do SN1. And the most challenging decision here is if we have secondary alkyl halides, because this is kind of a gray area, these can do either SN2 or SN1. So if we have a primary alkyl halide, we know what mechanism it will be. If we have a tertiary alkyl halide, we know the mechanism. But if it's secondary, we're going to have to look at other reaction components to make our prediction. The strength of the nucleophile plays a strong effect on the mechanism as well. In general, if we have strong nucleophiles, which tend to be anionic, those are going to favor SN2. If we have weak nucleophiles, and these are usually neutral, this is going to favor SN1. In fact, SN1 reactions really only take place with nucleophiles like water or alcohols or maybe carboxylic acids. Notice that these are also solvents, and these are polar protic solvents. So when our nucleophile is also our solvent, then we have a situation that is called solvolysis. This is when the nucleophile is also the solvent. And we see this most often in SN1 reactions. So let's look at the reaction we have here and the two different conditions. Notice in our reactant, we have a secondary alkyl halide, so this tells us that this could go either SN2 or SN1. So the next thing we have to look at are the conditions, are the nucleophile. So in the top pathway, we have a strong nucleophile, and so that favors SN2. And because it's SN2, we know that this will also lead to inversion of configuration. So when we consider the product here, we know that the methyl group, the stereochemistry of this methyl group, is remote from the reaction site, and so it's going to remain unchanged. So it's going to be going up like this. Because we have inversion of configuration, this hydroxide is going to come in from the back and displace the bromine. So that means that the bromine, or the alcohol, is going to be back. So the easiest way to draw an inversion is if one group has a wedge, the new group will have a dashed line. All right, let's look what happens if, instead of using hydroxide, we use water as the nucleophile. So water is a weak nucleophile, and so this will support an SN1 mechanism. We know that SN1 gives us a mixture of stereochemistry. All right, so let's just draw out how this would go. I'm going to fit it in down here. So remember, the first step of this is just loss of the leaving group. So I'll just draw this in green. So the leaving group comes off. This one, methyl group, is still unaffected, and we get a carbocation at this position. The nucleophile, the water, can then attack from the top or the bottom. And this gives us two more intermediates. This methyl group remains unchanged. If the water molecule comes in from the top, we're going to attach a water molecule right here. This oxygen, because it now has 3 bonds, it's like hydronium ion, has a plus charge. The other intermediate has the trans stereochemistry here, like this. All right, so these aren't our final product, though, because they're not neutral. So to get to the final product, we need to remove a proton on that oxygen. And the most abundant possible base to remove that proton is just water. So water is going to remove this proton here. This is just an acid-base reaction, giving us one of our final products. Methyl, so this one has the cis, so this is really what we would call retention. And if we do the same thing for this other intermediate, water acts as a base, removes that proton to give us a neutral final product. And this one is inversion. And remember, when we do an SN1 reaction, we get a mixture of retention and inversion. So let's consider here, though, let's look at these two. What's the relationship between these two products? All right, are they chiral? No, they're actually not chiral because there are no stereogenic centers. But they are stereoisomers of one another. One is cis and one is trans, and they are not mirror images, and so these are diastereomers. Any good leaving group will favor both SN2 and SN1 mechanisms. And so this really doesn't help us much in trying to discern which mechanism is taking place. Solvents are a little bit better, but this is really more of a supporting issue rather than one that will determine the mechanism. In general, SN1 mechanisms are favored by protic solvents, and so these are things like water and alcohols predominantly. And like we saw, or like I mentioned before, when these are actually the nucleophile as well, this would be solvolysis. SN2 mechanisms are favored by aprotic solvents. These are solvents like DMSO, DMF, and acetone. One exception to these rules is when we use nucleophiles that look like this. Okay, this would be called methoxide. Right? It's just like hydroxide, but we've replaced the hydrogen on hydroxide with a methyl group. When we use a nucleophile like methoxide, we usually run the reaction in methanol as the solvent. So notice that we have this pair of methoxide and methanol. If we were to use this species as a nucleophile, so this is 2 carbons, so ethoxide, we would use ethanol as the solvent. So the alkyl groups typically match in these cases. But because the nucleophile is strong, these combinations still favor SN2. This slide gives a summary of all of the things that we've just mentioned, and I'll leave it up to you to read through this and make sure you understand these. Let's try to put this all together and do 2 things. First, we're going to predict the mechanism, and understanding the mechanism, we're going to predict the products. The first thing that we'll always look at is the alkyl halide. The first reaction, we have a secondary alkyl halide. And so we know that the reaction could be either SN2 or SN1. Okay, so we haven't really decided anything. So the next thing that we'll look at is the nucleophile. And in this case, water is the nucleophile. And so this is weak. And so this supports an SN1 mechanism. So when we have an SN1 mechanism, we know that we will get a mixture of products. If the products are enantiomers, then that mixture will be racemic. So our 2 products are like this. If water is the nucleophile, then our product will be an alcohol. All right, so we get one that has retention, and the other product will have inversion. So this would be a racemic mixture because there's a single stereogenic center. All right, let's look at the next one. What's the substitution of that leaving group? We have an iodide. Okay, that iodide's bonded to a carbon that is attached to 3 other carbons, so this is a tertiary alkyl halide, and we should know that tertiary alkyl halides can only do SN1 substitutions. So the first step in this mechanism then is for the leaving group to come off. Let's draw out this mechanism. That will give us a carbocation that looks like this. The nucleophile, which is methanol, will use its pair of non-bonding electrons to either come in from the top or the bottom. That will give us 2 possible intermediates. All right, if it comes in from the top, we're going to have this intermediate, so we have to incorporate the entire methanol molecule there. The other possibility is with that stereochemistry reversed. So this will be going back. There's the H. Can hardly fit this in here though. CH3, and here's the methyl group. This has a plus charge on it. And so to get to our final product, we need to remove a proton from that oxygen. So like we saw on the previous slide when we were using water, now methanol with its non-bonding pair of electrons is the most likely base, partly because there's just so much of it. It's behaving as a solvent here as well as a nucleophile. So the methanol removes that proton, and that gives us one of our final products. Like this. We can do the same thing to the other intermediate. Methanol will remove that proton. Remember, those arrows are showing the movement of electrons, not the movement of atoms. And in this case, the methoxy group is OCH3 is going back, and the methyl group is coming forward. All right, so in this case, these would not be enantiomers because, in fact, we have two other chiral centers, or stereogenic centers, that we haven't really mentioned what the stereochemistry is there, but so these two would be diastereomers because those two centers would match, and the new one that we just generated would be different. All right, one more on this page. So here we have a secondary alkyl halide. This could give us either SN2 or SN1. We have a charged strong nucleophile, and we have an aprotic solvent. These two things together suggest an SN2 mechanism, which will give inversion of stereochemistry. So to draw the product for that, we'll just draw our carbon skeleton, and our new group, our nucleophile, will be bonded in the opposite direction of the leaving group. And so this is going to be a wedge and an SH right here. So in each of these cases, of course, if we wanted to be complete and balance things, then the leaving group would be over here. But oftentimes what we do in organic chemistry is we focus on that organic product. All right, three more examples. We can't do really too many of these, right? So in the first problem, we have, let's look where the bromine is attached. This is a primary alkyl halide. Primary alkyl halides only do SN2. All right. The reason for that is for one thing, it's not very sterically hindered for the nucleophile to attack at the carbon bearing the bromine, and if the bromine were to come off, primary carbocations are so unstable that they never really form. So this would be SN2. There's no stereochemistry at that position. So it is inversion, but we don't really see the difference. And our nucleophile here is this methoxide. So we're just going to add an oxygen and an ethyl group. All right, so notice that even though we have a protic solvent, this is still an SN2 substitution. The second one is a secondary alkyl halide. This is a charge. This is cyanide, and it's a good nucleophile, strong nucleophile. Notice we also have an aprotic solvent. Okay, so these support SN2. So like we did before, this methyl group is remote to the reaction, so its stereochemistry stays untouched, stays the same. We get inversion, and so we go from the trans reactant to the cis product. Our final example, similar to that, we have secondary, we have a strong nucleophile, we have an aprotic solvent. This should be SN2 as well. And so our product will have this isopropyl group unchanged and an inversion of stereochemistry to give us this product. So hopefully this discussion will help you to determine mechanism and then predict products.